Okay, so hello students, welcome to EEEE Lecture number 25. We have to solve two more numericals based on parallel RLC circuit. That will be numerical number 17. So let us write the given data over here. Numerical number 17, that is. So that is number 17. So we'll write the given data. A coil having a resistance of 50 ohms and inductance of 0.02 Henry is connected. So these two are a coil, right? So what do you mean by a coil? We have a resistor and we have a series inductance. What are the values? 50 ohms and 0.02 Henry. Okay, this is L, this is R, or we can call this as a small r, because if it is a coil we can call it as a small r, is connected in parallel with a capacitor of value. What is the value of the capacitor? 25 microfarad. So this is connected in parallel with a capacitor whose value is 25 microfarad. So this is C, okay, and it is connected across a 200 volt 50 hertz supply. So it's connected across a 200 volt 50 hertz supply. This is 50 hertz, 200 volt RMS value. All right. And what do we need to find? We need to find the current in the coil and the capacitor, total current drawn and power factor, total power consumed by the circuit. Alright, so what all things do we need to find out? We need to find, first of all, let us define these branches. Let me take this as a full screen. Okay. Yeah, this is fine. Now let me define the two branches. So the first RL coil, RL branch, we can call it as a coil, and that we define as impedance as Z1. Second branch we call the impedance as Z2. Alright, and let us say the current flowing through branch Z1 is I1 and through Z2 is I2, and this is my total current I. So basically my total circuit current I is I1 plus I2. Now since this is a parallel network, my voltage V is common between the both, right? So V is equal to I1 into Z1, and that is also equal to I2 into Z2. So how will you find I1 and I2? I1 will be V upon Z1 and I2 will be V upon Z2. So that is what we need to find out. What was asked? To find current flowing through the coil. So we need to find I1, I2, current flowing through the capacitor. Then we need to find the total current I and the power factor. And third thing, we have to find the total power, active power P. Alright, so let's start with a numerical. So first of all, we will start by solving the values of, start by expressing finding the values of Z1 and Z2. Okay, so what is Z1 here? Z1 is given by small r plus jxl, right? So r plus jxl, is it correct? And Z2 will be, it is r is not present, so it will be 0 minus jxc. That's the standard form, right? So since it is capacitive, it will be minus jxc. Since it is inductive, it will be plus jxl. So that means we need to find the value of xl and xc, okay, for these two equations to be written. So let's find the value of xl. So xl will be 2 pi f into L. F is 50, so that will be 100 pi into 0.02. And I guess we have calculated this in the class. It was 6.28 ohms. Alright. Then second thing we calculate is xc, which is 1 upon 2 pi fc, which is 1 upon 100 pi into 25 into 10 raised to minus 6. How much was this value coming in your class when you solved this? 127.32, right? Correct? Yeah. So next we find the value of Z1. We rewrite the equation. So R is given as how much? R is 50 ohms. So it will be 50 plus J. 6.28. Okay, so this is in rectangular form. We can convert this into, we can write this Z1 bar, Z1 bar. We can convert this into polar form by pressing shift polar in your calculator. So that will come out to be 50.39 at an angle 7.16 degrees, and similarly Z2 will be 0 minus j xe. So this is 127.32. So this is in rectangular form. We need to convert this into polar form by pressing shift polar, shift POL in your calculator. So that comes out to be 127.32 at an angle minus 30 degree, minus 90 degree, right? Minus 90. I guess you are getting the same values, right? Okay. Now, why did we calculate in polar form? Because over here, if you see, these we have to divide. Okay, so we can divide when their quantities are in polar form. Now, let's proceed forward. So, I am going a little fast because this we have covered in the class. So, V upon Z1 bar. How much is V RMS value? It's 200. So, 200 angle 0 divided by 50.39 angle 7.16 degree. So how much is this? 3.97 at an angle minus 7.16 degree. So this many amperes. Alright. Then next we calculate I2. Similarly, it is V upon Z2. That will be 200 at an angle 0, and Z2 is 127.32 at an angle minus 90. So this becomes 1.57, is it? 1.57 at an angle 90 degree. Okay. So we got the value of I1 and I2, current flowing through the coil, current flowing through the capacitor. Now we need to add these together. That's why we need to convert this again into rectangular form. So you can press shift rec in your calculator, shift rectangular. So this rectangular form will be 3.94 minus 0.49j, correct? Is it this only? And this will be 0 plus 1.57j. I hope the rectangular coordinates are matching. Now why we are converting into rectangular form? Because we need to add these currents. So total current I in the circuit will be I1 plus I2. Now we add these together, 3.94 minus 0.49j plus 0 plus 1.57j. So how much this comes out to be? 4.08, right? No, not 4.08, sorry. It's 3.94 plus 1.08j. Okay. Now we need to establish the relation between current I and current voltage V. So we need to convert it into polar form again. So you press shift polar POL in your calculator. Shift polar 3.94 comma 1.08. So how much is the value? 4.08 at an angle how much it is? 15 points. 328, that is 33 amperes, correct? Okay, and this is in the standard form. There is a standard form to follow this in current I RMS at an angle phi. Alright, and what was the value of V? 200 at an angle 0. So what is the phase difference between V bar and I bar? It's phi. So how much is phi over here? How much is my phase angle phi? 15.33 degrees. Okay. Now next we need to find the power factor. So power factor of the circuit is cos phi. So cos of 15.33. How much is that? 0. How much? 93 something? 9? Okay, 964. Okay, fine. Remember, power factor always will be between 0 and 1 only. So last thing we have to calculate is active power. That will be VI cos phi. Voltage RMS is 200. Current is how much over here? 4.08, and cos phi is 0.964. So how much is this number? 786.62, right? Did you all get this number? Okay. Oh, is it? Okay. If it is there, even though we have calculated, it's fine. No, it's given total current drawn and power factor PF. See, so can we check the values over here? All the values are matching properly. Okay. So now we come to the last numerical for series RC parallel RC, series RL parallel RL, series RLC parallel RLC. So all the numerical combinations are covered with this 18th numerical. So let's read it. For a circuit shown below, calculate the impedance and admittance of each branch. Calculate the equivalent admittance and impedance of the circuit, supply current and power factor. So first of all, let's redraw the circuit and then calculate it one by one. Alright. So let me just take this and redraw it. Please you all also redraw it in your books. Okay, so this is numerical, last numerical for this topic. Then we'll start with series RLC resonance. Okay, so let's redraw it the way it is there. So we have R1 L1 value given to you. This is 5 ohms. This is 0.05 Henry. Next, it's in the series combination of RL is in parallel with RC combination. So there is a resistor and a capacitor. Okay, and they have been supplied with how much is the voltage? 100 volt, comma 50 hertz. Okay, the current in the circuit is I, which is the AC current, and this R2C1 value is how much? 10 ohms, 100 microfarads. Okay, so first of all, we will write down what we need to find out. Before that, we will mark the branches impedance. So this, let's say this R1 L1 we call it as Z1 branch, impedance of this is Z1, and this R2 C1 is called as Z2. Okay, all right. So what is to be found out over here? Let us write it down. To find admittance of each branch, calculate impedance and admittance of each branch, right? So what do you mean by impedance and admittance? We need to calculate Z1 and Z2. And what is admittance? Y1 and Y2. Correct? Yes or no? Hello? Then we have to calculate equivalent admittance and impedance. That means Z equivalent and Y equivalent. Total admittance and impedance. Then we need to find the supply current. That will be the current I and also the power factor of the circuit. Okay, so this is the given data. So let me put it to full screen now. Someone wants to join the meeting, let them join in the Somaya email ID because yeah, admit. Okay, okay, fine. So have you drawn this? Can we start now, everyone? Okay, so let's start together the solution. So first of all, we'll write first step. Um, what is Z1? Can you tell me? It's R1 plus J XL1. Okay, it is not L1, it is XL1. Please remember that. All right. Then secondly, what is Z2 given by? Can you tell me this? What is Z2 on the same line? Yeah, absolutely correct. R2 minus because it is capacitive. Now for this, we need the value of XL1 and XE1. So let's find the value of XL1, which is 2 pi FL1, which is F is 50 hertz, so it will be 100 pi. L1 is 0.05. So let me know the value of XL1, how much it is. You can have, so 15.71 ohms is the answer. Also, we need to find Xe1, which is 1 upon 2 pi Fc1, which is 1 upon 100 pi into 100 microfarad. So 100 into 10 is to minus 6. Let me also know the value of Xe1. How much? Yeah, Xe1 31.83 ohms. That's perfect. Now we'll split up these values over here. Let's continue writing. So Z1 will be, Z1 bar will be R1, right? So how much is R1? 5 ohms. Z1 will be 5 plus J 15.71. Okay, ohms. We need to find its, I mean, polar form. So what is the polar form? You press shift polar 5 comma 15.71. So what do you get over here? 72.3. That's correct. Next we calculate the value of Z2. Z2 is 10 minus J XE1, that is 31.81 ohms. So convert this into polar form and calculate the value of Z2. So press shift polar 10 comma minus 31.83. How much did you got this? 33.36 at an angle minus 72.5. Okay, that's correct. Now, so we have calculated the value of Z1 and Z2. Remember, the Z bar is Z angle phi. So we know Z1 is how much? How much is Z1 from here? Only the magnitude, 16.48 ohms, correct? And Z2 is 33.36 ohms. So this is angle. That is why we have written bar, vector. Now, how will you calculate Y1 bar? Anyone? Admittance. It is, yeah, 1 by Z1 Z1, that will be polar form. So 1 divided by 16.49 angle 72.3. So how much is that? Is it 0.06 at an angle minus 72.3 degrees? Mo. Unit is mo. Okay. Next we calculate the value of Y2, that is 1 upon Z2. So 1 upon 33.36 angle minus 72.5. So how much is this? Okay, 0.03 angle, it will be plus. Okay, yes. Now, so we found out the value of Z1, Z2, Y1, Y2. Next, we have to calculate Z equivalent. So can you tell me what is Z equivalent? Z1 and Z2 are in parallel. So what is Z equivalent? How will you find Z equivalent? They are in parallel. So one technique is 1 upon Z equivalent is 1 upon Z1 plus 1 upon Z2. Yes or no? Hello? Can we write the same thing? What is 1 upon Z equivalent? Z equivalent? Y equivalent, right? And 1 upon Z1 is Y1 bar plus Y2 bar. So first we calculate Y equivalent. Then Y equivalent will be 1 upon Z equivalent. So let's calculate Y equivalent. So how much is Y equivalent? It's y1 plus y2. So can we add y1 and y2 in polar form? No. So let's convert this into rectangular form because it cannot be added. So convert this 0.06 minus 72 into the polar, the rectangular form. How much it is? 0.57. Yeah, that is more. And over here, 0, 0, okay, 0.285J. Okay. Now we have to add these two quantities. So 0.018 minus 0.057J, this will be plus 0.0089 plus 0.0285J. Now add these two quantities. So you get 0.027 minus 0.0285J, right? Did you get this answer? Convert this into, now convert this into polar again. How much it is? So press shift polar 0.027 comma minus 0.0285. How much did you get? 0 point at an angle. Okay, and the unit is mho. So this is my Y equivalent, the admittance equivalent admittance. This is the answer. Now, how will you find Z equivalent? 1 upon Y equivalent is Z equivalent. Yes or no? So you calculate this 1 upon 0.04 at an angle minus 46.55. So how much did you get? Tell me. This will be 25 something at an angle. How much exactly? Okay, 25 angle 46.55. So this is my equivalent impedance of the circuit. Okay, Z equivalent. What else to find? Current, right? Supply current and power factor. So tell me, how will you find supply current? Oh, this is challenging. Can you tell me how will you find supply current? Okay, let's go over here in the circuit. Tell me what is supply current. Total V is how much? No, 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 no. V is 100, but V is I into Z equivalent, right? Correct? So what will be I? V upon Z equivalent. And what is 1 upon equivalent? V into Y equivalent. Yes or no? We can use any of these two formulas, either this or this. So you can use either this or this. Both are correct. So let's go for the circuit current. So circuit current I is given by, let's go for the familiar term, Z equivalent. So V is how much? 100 angle 0. Z equivalent is how much? 25.64 angle, I think, sorry, 25, right? Sorry, 25 at an angle 46.55, right? How much is the answer? What's the answer to this? Minus 46.55. Okay. So this I is in the form I angle theta. So what is the phase difference between I and V? Is plus or minus? Minus 46.55. So how much is phi then? Minus 46.55. Last we have to find the power factor, it seems, right? So power factor is cos phi. So cos of minus 46.55. So cos of minus theta is cos theta only. So let me know this final value. 6, 9. Okay, correct. So please verify all the answers. So with this we complete series RLC, series RC, series RL, parallel RC, parallel RLC, and parallel RL circuits and their numericals analysis. Okay? Yeah, we have done. Yeah, we can do Z1 plus Z2. Absolutely. But since Y equivalent was available, that's why we use this formula. No, Z1 plus Z2 ना ये वाला है ना, देखो पैरेलल में है ना. So 1 upon Z equivalent is equal to 1 upon Z1 plus 1 upon Z2. They are not in series. So you will get different only. Yes, yes. Parallel, if you do it, it's correct. Okay, everyone understood this? Okay, so let's go for the RLC series resonance circuit. I'll only take theory today. Numericals will start from the next week, Tuesday. Okay, so let's write down. I hope everyone has completed, whoever is present over here. Okay, so now let's start with RLC. So you can write along RLC series resonance circuit. So what do you mean by resonance? Resonant means the ability of your circuit to transmit certain frequencies. At what particular frequency it will pass all the frequencies and eliminate all the other frequency. That is what is resonance is. So let's say if my resonance is 20 kilohertz, so I only pass 20 kilohertz. If anything is less than 20 kilohertz frequency, I'll reject it. If anything is greater than 20 kilohertz, I'll reject it. So only passing 20 kilohertz is by resonance. Okay. So let's consider series RLC circuit. So draw RLC in series once again and connect it to the AC supply. So let's say this voltage is Vrms in hertz. This current is I. This is RLC. Okay. And the total impedance of the circuit is Z. This is Z. Okay. And the voltage across each of them, this voltage is VR, this voltage is VL, and this voltage is VC correspondingly. Voltage across resistor, inductor, and capacitor. So just say this is ZR, resonance, impedance at resonance. So in a series RLC circuit, we have inductance and capacitance also. So can you tell me when is the circuit capacitive or inductive? This is series RLC. ZR is the circuit impedance at resonance. I'll talk about resonance, but tell me now the conditions under which the circuit is inductive. Inductive. So when XL is greater than XC, my nature of the circuit is inductive. And the other way around, XL less than XC, my circuit nature is capacitive. Okay. So here total voltage V is the vector sum of VR plus VL plus VC. This much you agree, right? And the same current flows through all the three circuit elements R, L and C. Okay. So here, according to this, whichever is higher, so Z will be given by impedance will be given by R plus JX. Okay, X will be XL minus XC when it is inductive. Okay, so it will be XL minus XC when it is inductive, and this will be XC minus XL, right, when it is capacitive. So the net reactance of the circuit will be net reactance X, that is X will be given by mod of XL minus XC, whichever is greater. Okay. Now, if I draw the phasor diagram for this RLC series circuit, do you remember? So let's say we have a current on the x-axis. So tell me, where will I draw VR? Just the phasor diagram. Yeah, same axis over here. So this is VR. It's in the same direction as I, current. Where will I draw VL and VC? That's correct. And let's say VL and VC are same. Let's say for a condition VL and VC are same, and that is actually resonance condition. So this is VL, this is VC. When they are same, the phase angle of the circuit is how much now? Can you tell me the equivalent? Zero. Absolutely correct. So here, whenever VR is equal to VC, this happens at resonant frequency only one. F equal to FR. FR is the resonant frequency. Okay. Here, my phase angle of the circuit is zero. And what is my power factor? Oh no, not VR. VL. 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 Yes, absolutely. So power factor 1 is the most desirable form. And here, can I say VR will be equal to V? Can I say this? Because circuit is becoming resistive now. Neither it is inductive nor it is capacitive. Yes or no? Hello? Okay. Now tell me, we are building on the concepts. So next concept is, how much is XL? 2 pi FL ohms. How much is XC? 1 upon 2 pi FC ohms. So can I say both the, acha, what is XL called as? Inductive reactance, right? So can I say XL is proportional to the supply frequency, yes or no? And XC is inversely proportional to the supply frequency, yes or no? Yeah. So now at resonant frequency, so FR is resonance frequency. At resonant frequency, the inductive reactance XL becomes equal to the capacitive reactance XC. So this is number one condition. Therefore, the net reactance of the circuit X will be XL minus XC, which will be 0. Yes or no? And if I want to write a total impedance of the circuit at resonance, what it will be? R plus minus J. So what will be the impedance of the circuit now? Tell me. R. Agree? So the circuit has become purely resistive at resonance. Agree or no? The circuit is purely resistive since ZR is equal to R now. So when the circuit is purely resistive, current I is in phase with the applied voltage V. Power factor is unity. So these conditions result in electrical series resonance. So what are the conditions? Let me know. Again we revise. What are the conditions? Number one, this. VL is equal to VC. Phi is 0. These are consequences. Power factor is unity. XL is equal to XC. Net reactance of the circuit is 0 and ZR is equal to R. So these are all the conditions which makes the series resonance. So these are all series resonance conditions. Series resonance. Getting it? So now what is the effect of series resonance? This is the effect actually. The effect of series resonance is that my XL is becoming XC. That is true. My impedance at resonance. Can I say impedance at resonance is how much now? Is it minimum or maximum? Can you tell me? ZR is minimum or maximum? Yes, is minimum and equal to resistance of the circuit R. Yes or no? So we can say ZR is equal to R ohms. So if my impedance is minimum, what about the current? Yes. So current at resonance, IR is the current at resonance is maximum. Given by the formula, IR is V by ZR, and so it will be V by R. Correct? So current in the circuit is maximum. So as the current in the circuit IR is maximum, power absorbed by the circuit also will be maximum. So P also will be maximum, which will be given by I square at resonance into R. That is P max. Understood this? Hello? Are you following so far? Shall I continue? You are noting it down something? A year? Okay. Yeah, we have few more concepts remaining, around 10-15 minutes remaining, then we are done with today's lecture. Okay, can I continue now? Yes. Now we'll talk about resonant frequency. What is resonant frequency? Denoted by FR. Okay, so XL, we can say XL and XC are frequency dependent, right? Yes or no? What is the relation? XL is equal to actually 2 pi FL. So XL is proportional to F and XC is 1 upon 2 pi FC. So you can say XC is inversely proportional to F. Okay. So if I have a graph like this, if I have a graph of frequency versus impedance, right? So where will be my how will I plot my XL curve? XL is proportional, right? So this will be XL. Yes or no? Yeah. How will my graph of, mathematics, right? Inversely proportional. How do you show? You show it like this, right? Yes or no? Inversely proportional. Did you show it like this or no? This is XC. This is an important concept coming up. So where they intersect? Will they intersect only at one point or many points? XL and XC become intersect at one point or many points? Tell me. What do you see on the? So they intersect only at one point, right? So this is called as resonance frequency, FR. So when XL is equal to XC, then resonant frequency happens. And there is one more line for the resistance. So this straight line is resistor R. Okay. So this is frequency versus impedance of the circuit. So as you can see, the higher the value of frequency, which is higher, at higher frequency, what is high? XL is high, right? Yes or no? And at higher frequencies, XC is low, and vice versa. At lower frequencies, XL is low and XC is high. So we'll write the formal statement of resonant frequency. The frequency at which inductive reactance is equal to capacitive reactance, that is XL is equal to XC in a series RLC circuit is called resonant frequency. We'll write it in the formal definition. Resonant frequency, FR. Alright. Now we'll derive the expression for FR. Okay. So we write at series resonance, XL is equal to XC. Agree? So we can, what is XC now? XL now 2 pi FRL, resonant frequency, right? It is 1 upon 2 pi FRC. So this is the resonant frequency. Can I take it over here? FR square equal to 1 upon this 2 pi, I'll take it down. So it will be 4 pi square, agree? Into LC. Yes or no? So can you tell me what is resonant frequency FR? You take the square root. So it will be 2 pi square root of LC. That is the formula. Very, very important for numericals. This is in hertz. This is for series RLC resonance. Okay, and this is my resonant frequency formula. Please note it down. Very important. Can I write it in a different way? Can I write it in omega r form? What is omega r? 2 pi fr, correct? Radians per second. So how will I write this? 1 upon square root of LC. Agree or no? What's the unit over here? Radians per second. So we can write both the ways. Please note it down. Now we talk about two more parameters, that is resonance curve, and then we'll stop the lecture for today. We'll talk about series resonance curve. Up till here completed, everyone? Yes, no? Okay, great. We are just a few minutes away. Now we have talked about resonant frequency. Now let's talk about series resonance curve. So, okay, no. Series resonance curve. Okay, it is a curve of between circuit current I and F frequency. Okay, so I will draw the current in the y-axis and frequency on the x-axis. Now, current reaches the maximum value or minimum value at frequency. What did you tell? Current is maximum at resonance. Yes or no? So that means at F equal to FR, my current will be maximum. Yes or no? So let's say this, we define this maximum point over here. So the current will vary like this. This is my resonance curve. So first let me just draw the curve and then define this. My curve will look like this. This is my resonance curve. Please draw it. So this is F equal to FR, resonant point. This is maximum current, I max. Acha, can you tell me the maximum current formula? IR, it's V by R. Resonance current, maximum resonant current is V by R. Is my power maximum over here? Yes. So maximum power is I square into R. Okay. So this is the resonance curve. Can you tell me at lower frequencies what is happening? So XL is proportional to frequency, XC is inversely proportional to frequency. So at lower frequency, what is the case? Lower frequency, which is greater? XC is greater than XL, yes or no? And at f equal to fr, xc is equal to xl. And at higher frequency, what happens? XL becomes greater than XC. Yes or no? Hello. Yeah. So, if my frequency F is less than resonant frequency, can I say my nature of the circuit is capacitive or inductive? What is the nature? For lower frequencies than resonant frequency, what is my nature of the circuit? Capacitive, right? Yeah. So on the left hand side of the curve, it's capacitive. Any frequency higher than the resonant frequency, XL becomes greater than XC, right? So the nature of the circuit is inductive. And at resonance, what is the nature of the circuit? Resistive. Clear? Is this crystal clear? And the magnitude of the current falls rapidly if not in resonance. So maximum, the current will be maximum only at resonance. Either way, it will fall down drastically from resonant frequency. Okay, understood this? So now, if you have understood this, then it will be very easy to plot impedance curve. Impedance curve will be exactly reversed, right? Because impedance was inversely proportional to R only, right? Here in this case, can you see this? Impedance, here see, impedance was minimum, ZR was minimum. So ZR was inversely proportional to R. Oh, sorry, not R. V was equal to I into ZR. Okay. So here the impedance curve will be like this. Draw this, please. It will be minimum at resonance. So this is F equal to FR. This is frequency, and this is impedance Z. Okay. So now can you tell me here the impedance of the circuit is where for F, here also we can say na, for F less than FR, impedance of the circuit is capacitive na, and here for higher frequency it is inductive. What about the power factor when the circuit is capacitive? Power factor is leading or lagging? Leading. And here the power factor is lagging. What about at F equal to FR? At this point, resonance point, what is my power factor? Yes, power factor becomes 1. Everywhere else it is almost leading or lagging. Correct? Yeah. So we stop the lecture over here now, and we'll continue from here on in the next class, on Monday's class. Okay. So that's it for today. There are still some 10-15 minutes of theory topic remaining regarding series resonance circuit. I don't want to push it forward, so I want to discontinue today, and we'll resume it in the offline class. Okay. So thank you all for joining.